There we go. All right, so if you have a system where there's lots of masses and they're not all equal, and they're not all uniformly distributed, you can't just say the center of mass is at the middle. You have to figure out where it is. So it turns out you can find the center of mass using a simple little weighted formula. You can take each mass times its distance from the end, and then divide by the total mass. Now, if every single mass was the same and spread out equally, this would end up being the middle. Okay? Let's just try it. Grab your calculator. This is at 0. This is at 0.2 meters, 0.5 meters, and 1.1 meters. So, take each mass times its distance from the end and add them up. So 5 times 0 plus 12 times 0.2 plus 7 times 0.5 times 10 times 1.1. That's each mass times its position. So we're going to take each mass times its position and add them up, and we're going to divide by the total mass. So divide by the total mass, which is 5 plus 12 plus 7 plus 10. Anybody get an answer there? Luke, did you get one?
0.457.
0.45. So about here, that's the center of mass in the x direction. Okay? And if this was spread out in 2 dimensions, we could also find the center of mass in the y direction, taking each mass times how far it is in the y direction, adding them up and dividing by the y direction. And you could do the z direction. It was a 3-dimensional object. And it was a solid object, like some goofy stick that wasn't uniform. So if you had a piece of plywood, for example, that looked like this, you could find its center of mass. You could divide it into sections and treat each section as the mass of this section times its distance, plus the mass of this section times its distance, right? And add them all up, divide by the total mass, and you get the center of mass. Now, an easier way to find the center of mass is not to do it mathematically with that formula. It's just to hang it, okay? So if you take a weird-shaped object and you hang it, so if you drill a hole right here and hang it, it's going to rotate, right? If you hang it like that, it's going to look something like this. Right? Let's say I hang it from a string. It's going to hang like that, right? That means the center of mass is somewhere in that direction. And then if I drill another hole and hang it, I can find the center of mass is somewhere in that direction. And anytime you drill a hole and hang it, the center of mass will be directly below the place it's hanging from, and you can find the center of mass. So here's we gotta do an experiment. Let's go. Go on. Sorry, Albert, you stay. So you have a center of mass, and it's somewhere near your belly button, but internal to you, okay? About halfway between here and there, not quite. And that's your center of mass. And you got to keep that over your base in order to be stable. So when you walk, you are shifting your center of mass in fairly amazing ways to keep balanced. So what does it mean to be balanced? Well, to be balanced means your center of mass is over your base. If there's a truck and somebody loads it like this, its center of mass is over on this side, right? That center of mass needs to be over the base. Here's the base from here to here, right? What if they're on a hill and that center of mass shifts so that it's now outside the base? It will topple. The stability, something that's stable when the center of mass is over its base, okay? So, believe it or not, this goofy looking bird, have you ever seen those? Where's its center of mass? On its beak, okay? That's why it can balance at that point. So it's got mass to the left and the right, and it's got mass behind and in front of. That's why the wings come forward. It's engineered to have a center of mass right there. Okay? All right, now, are these two objects both stable? So we actually use two different words. Both of these objects would balance. Okay? This would balance, and that would balance. It would balance because the center of mass, where gravity is pulling, is over the base, right? But what would happen if you tip this a little bit? If I tip that a little bit, it would go up a little bit, right? But which way would gravity rotate it? Back down. So perturbations, or small disturbances, result in it returning to its balanced location, right? We call that stable. This is also balanced, but we say it is unstable, because a small perturbation will cause it to topple. So something is stable if, when you bump it a little bit, it goes back to where it was. It might be balanced, but unstable if a perturbation disturbs it and makes it fall. See the difference? You guys know what weebles are? Weebles wobble, but they don't fall down. Their center of mass is really low. They're heavy on the bottom, right? So if you give it a little bit of a push to the side, so now it's on its side. Here's the center of mass, and here's where it's touching the ground. If gravity is pulling down on the center of mass and it's touching the ground here, which way does the force of gravity tend to twist the weeble? Back up, right? And if you took them this way, here's the center of mass, gravity's pulling this way, and the pivot where it's touching the ground is that way, and so it tends to make them stand back up again. So that is called a stable point. Perturbations, disturbances, are returned to the original, okay? We do this with airplane wings. Airplane wings have what's called dihedral. They're actually not flat. They're up a little bit. So when you bank like this wing, because it's now horizontal, gives you more lift than this wing. And if this wing is giving you more lift, what will happen? It'll tend to right itself. So perturbations tend to be corrected automatically by the extra lift. So when an airplane wing, when your airplane turns this way a little bit, okay, it doesn't just keep rolling. You actually have to really carefully engineer if you want it to roll, like a fighter jet. But most airplane wings are up a little bit, okay? So that's about stability. Also, the center of mass of an airplane is very carefully calculated. If you fly a small plane, the pilot will probably say, what do you weigh? You sitting back. What do you weigh? You sit in front. They got to distribute their weight carefully. On a bigger plane, they have sort of more, it sort of averages out, but they also have to carefully load the luggage. But the center of mass needs to be somewhere slightly in front of the lift center, because the back wings actually push down, okay? And if the center of mass was here, that would tend to rotate it downwards, and the back control surfaces apply downwards. It tends to make the nose go up, right? So, okay, and we've already talked about this, but the center of mass If there's no net force on a system, the center of mass doesn't change its motion. The parts might smash into each other and rearrange, but if the center of mass of two cars is moving before the collision, it'll be moving the same velocity after the collision, right? So here's an example. The Earth and the Moon, they have a common center of mass, and it's actually about right there. And the center of mass is what the Earth and the Moon rotate around. The Moon doesn't just go around the Earth and the Earth sits still. The Earth actually kind of wobbles around their common center of mass. Both objects rotate around their center of mass. So that's what the Earth and the Moon system look like. This is called the Berry center, the center of mass of a two-body system. Okay? And it's that center of mass that follows a nice orbit around the sun, even though the parts are wobbly, right, as they go around the sun. All right, here's a question from an AP exam question a couple years ago. This is a tough one. Let's see. So, a 200-pound man is standing at the left end of a barge. So this is like a floating styrofoam. It can move. He's standing on the left end. This is 4 meters long, and the barge can freely float in the water. And this guy's 200 pounds, and the barge is 200 pounds. Okay? And it says the dock is 1 meter away from the side here. Okay? So, where is the center of mass of the man and the barge? That's the first question. How far from the dock is the center of mass of this system? So if you've got 200 pounds here, and 200 pounds spread across here, where's the center of mass of that system? You probably shouldn't need your calculator, but where's the center of mass of this thing? In its middle. So you've got 200 pounds here and 200 pounds here. Where's the center of that? Right here, right? How far is that from the dock? If this is 4 meters long, the middle's at 2 meters, right? So if you got 200 pounds here and 200 pounds here, the center of mass is right here, right? Which is 1 meter from the edge or 3 meters from here. So how far is the center of mass from the dock? 4 meters. Got that? Okay. The man walks to the other end of the barge. How far is the center of mass from the dock now?
4 meters.
What?
4 meters still.
Why?
Wouldn't the barge move this way? Let's see, like this way.
Why?
Is there no friction?
There is friction. The dude's got hiking boots on. He's got spikes. Anybody?
2 meters.
2 meters? You're just making that up. How far was the center of mass in part A?
4 meters.
4 meters. And what was it doing? Was it moving or sitting still?
Staying still.
Yeah, the center of mass is right here and it's not moving. Are there any external forces on this system? No. So can the center of mass change what it's doing? If the center of mass is at rest here, and there's no external forces on the system, then the center of mass cannot move. So it is still 4 meters. How is that possible? Well, as this guy walks this way, the barge moves that way. And the center of mass stays here. Okay? If your barge is floating on water and you walk this way, you're pushing on the barge with your feet to the left, so the barge moves to the left. So Matthew was kind of right. But the answer we're looking for is that you see, because there's no external forces on this system, its center of mass cannot move. So it's still going to be right here, 4 meters from the dock. So, question C. How far from the dock is the man when he reaches the other end of the barge? The center of mass is still going to be here, but the dude's going to be on the other side of the barge, right? So you're going to have the barge, the dude, the center of mass is still going to be right there, and this is still 4 meters from the dock, because the center of mass didn't move. So how far is the guy from the dock?
3 meters.
He's 3 meters now. You see that? I thought it was a clever question. Nobody got it. It was horrible. Like 19% of people got points on it. They haven't used it again. But hey, it's the idea. It's kind of fun. All right. If there's more than one force acting on a rigid object, to find the torque, you just add them up. Okay? When you add up all the unbalanced torques, we call that the net torque, which is exactly the same thing as we have when we had a net force, right? And lastly, to connect with lab yesterday, if you have something balancing and it's not rotating, then the net torque must be 0. That's what it means to be balanced, right? If something's balanced, it means that whatever's tending to make it twist this way is counteracted by the exact same amount of twist going the other way. It's balanced. So when we had in lab, when we had that meter stick and everything was all balanced, that means the net torque was 0. The twists to the left balance the twist to the right. And how do we find the twist to the left? We took the force and we multiplied it by the distance, right? We were finding the torque. Okay. What's the mass of the boy? This was an AP question on the multiple choice section. Go ahead, get your blankie, your calculator. Makes you feel better, even though you don't really need it. You can do it in your head. All right, Noah's got this. Did you do it in your head?
No.
Ah.
I'll wait for him. I haven't used it. But I'm just, if he's going to do it, why would I also do it?
Oh, I don't know.
Is that?
What do you got, Noah?
I'm still thinking. Give me a second.
What?
20.
20?
Yeah. I was checking my work and then someone said it, so now I look like I didn't
Oh.
AJ agrees also.
Okay, so this is 10 kilograms. Now, technically, you need to multiply by 9.8 because torques are forces. Okay, so if somebody said, what is the torque caused by this? You would say it's 100 newtons times 4 or 400 newton meters. But because everything is multiplied by g, we can ignore the g's. Okay, so 10 times 4 is 40. 5 times 8 is 40. So there's 80 units of torque going in the clockwise direction. So there must be 80 units of torque going in the counterclockwise direction. Do we have to worry about the bar? Why not? Where is its mass acting? On the pivot, so the bar is not contributing any torque. So, whatever this guy's mass is, times 4 has got to be 80. And 4 times what gives you 80 without a calculator? 20. There you go. That's not so bad, right? All right. I don't want to do that one. Okay, so now, let's put this together. Where the heck is my other? Here it is. So we're going to use this idea to talk about rotational statics. So, quick review. Torque. To find the torque, you take the force. So if I've got a rigid object, and it's pivoted right here. See the P? That means that's my pivot. I've got a rigid object. I'm going to apply a force. The torque will equal this force times this distance times the sine of that angle. Okay? Now, one way to think about it is this. can you imagine that force continued acting? Applying the force at this point, that far from the pivot, gives you the same torque as if it was perpendicularly applied that distance. Okay? This is going to be F times R times the sine of theta. If this is R, and that's theta, this length is R sine theta. So the perpendicular moment arm, you get the same torque if you take this force times this distance times the sine of theta, or if you just take this force times that distance, because that distance is R sine theta. It's the shortest distance between the line of the force and the pivot, the perpendicular moment arm. Okay, you get the same torque either way. Okay? So how you do it is up to you. So, we can cover that. Here's the idea. Let's quickly review. Remember back in the old days, by which I mean October, we said that if you've got a problem and the sum of the forces add up to 0, that must be true in every direction. Must be true in the y direction and the x direction, right? I mean, if something's not moving, the forces are balanced in every direction. So that means that some of the forces in the x and y add up to 0. So we could solve problems like this. Remember these?
Yeah.
So this I just snagged from the old one. Whatever force is going down, the exact same amount of force must be going up. And so the part of this force going up and the part of that force going up must add up to the force going down, which is 150 newtons, right? And then the force going to the right must equal the force going to the left. If they weren't equal, this thing would move. But if it's static, if it's not moving, the forces must be balanced, right? So we said that some of the forces in the direction, some of the forces are 0, so some of the forces in the x are 0. So that means the horizontal component of this, t cosine theta minus t left cosine theta equals 0. And then we did it in the y direction and we solved the problems. You guys vaguely remember this? Okay, we're going to use the same idea, except now we're also going to think about the fact that if it's a rigid object and it's not moving, not only must the forces be balanced, but the torques must be balanced too. Okay? So, when a rigid object is not rotating, when it's static, whether it's a ruler with some weights hanging on or anything, the torques must be balanced. They must add up to 0. So whatever torque is causing this thing to twist this way, it must be balanced by a torque causing it to twist that way. So the torque, the positive torque, the thing that's tending to rotate this object to the positive direction, is this mass times this distance. So if I take this mass times this distance, that's positive, minus this mass times this distance, it's got to equal 0. It's got to add up to 0, the net torque, okay? That's the idea. So we're going to look at statics. This is our big thing for today and tomorrow. The torques must add up to 0, okay? This is the condition for rotational equilibrium. So, if a rigid object is not rotating and it's not translating, so it's not turning and it's not moving, then the forces must add up to 0, both in the x and the y direction. And the torques must add up to 0 for every possible pivot. Okay? And that gives us an equation for every pivot we look at. So let me solve an example. I have time for an example here. And I'll do one more tomorrow, and then you're going to solve a bunch of problems with rotational statics. And if you take civil engineering, decide to be a civil engineer or a mechanical engineer, there's an entire course at Purdue called statics, where you just do this for like an entire bridge, right? And if you build a bridge, a suspension bridge, the forces better add up to 0 for every single point, right? So you got to use that to decide how thick to make each rope and each piece of concrete and how strong it's got to be to make sure that it can withstand the forces on it so that you don't get any unbalanced forces. All right, so let me solve this problem. I'll solve it here so that Aubrey can see. All right, so the first thing we're going to do is you're going to make a rigid body diagram, okay? And we are not going to try to save paper doing this, okay? So make a nice big diagram. Here's what I have. I have a rigid object. it's the board. So there's my rigid object. Okay? I'm going to draw the forces that are acting on it. Because this board has a mass m, there is a force at the middle pulling down, which is mg. That's the weight of the gravity. That's gravity pulling on the board. It acts at the middle. Okay? There is also a box here. And so there's a force pulling down here, which is capital Mg. And there are ropes on either side pulling up. So there's a force on the left. That's the tension on the left. And there's a rope on the right. That's the tension on the right. Okay? That is a rigid body diagram. It shows the object of interest and the forces. Okay? Before we had a free body diagram, we treated the body like a point. But now we can't because it might rotate, right? All right, what is your guess? Which of those two strings will hold more of the weight? You think the one on the right? Yeah, I mean, if you move this over more and more and more, this guy's going to have more of the weight, right? So we expect TR to be greater than TL. All right, now, we're going to apply our ideas. So first of all, this thing is not moving, so the sum of the forces acting on it must equal 0. That's true in the x and the y direction. Are there any forces in the x direction? Okay, so let's do the y direction. So the sum of the forces in the y direction must be 0. So which forces are going up, Noah? T left plus T right are going up, minus little mg minus big mg. That's got to equal 0, right? Is that enough information to solve for TL and TR? Can you find the tensions in the ropes? You can't. So now we need to get another equation. The y problem is not going to help us here. There's no forces in the y direction, right? So we're going to have to look at torques. The sum of the torques about any pivot must also add up to 0. Now here's the cool thing. You can pick the pivot. You can imagine any pivot you want. If you think about this as the pivot right there, is it rotating about that point? Nope. So the torque's got to add up to 0. Could you think about that as the pivot? You could. Is it rotating about that point? Nope. So the torque's about that point have got to add up to 0. You can pick any point you want. Here's the cool thing though. If I pick this point right here, does that force cause a torque? Does that force right there cause a twist around this point? It doesn't. So it'll not be in my equation. So if I want to eliminate a force, if I'm trying to solve for the left force, I could choose that as my pivot, and then the right force wouldn't be in my equation. So let's make this our pivot. So you need to make sure you define it on your diagram. That's the pivot. So if I'm going to say the net torque about the pivot equals 0, I've got to show what the pivot is. Now, think about this as your pivot. Okay? You've got a rigid object, and it's pivoted right here. So which forces tend to rotate it in the positive direction? Yeah, this mg would tend to cause it to rotate that way. That's the positive direction, right? So we're going to have capital Mg, and how far from the pivot does it act? 3 feet. Okay? So times 3. Plus, Mg is also a positive torque. It tends to rotate this board, right? You imagine this board, and we're thinking about this is the pivot. The weight of the board itself tends to rotate in the positive direction. So it's plus little mg, and how far does that act from the pivot? How do you know that? Alex? It's uniform, so its center of mass is at its middle. There you go, which is 4. So big mg times 3 plus big mg times 4 feet. I guess I should put feet there. Minus, see now this one here tends to rotate it in the counterclockwise direction. So minus the tension on the left times how far does that act from the pivot? 8, right? Times 8 feet. That's all got to add up to 0. Now, since I tell you the masses, a 20 kilogram box is put on the left end of a board, the mass of the board is 4 kilograms. You now can solve this for TL, right? The tension on the left. Once you know the tension on the left, you can go back here and find the tension on the right. See the strategy? So we're just going to develop systems of equations which we can solve using the idea that the net force is 0, but also the net torque is 0. Now, I'm going to go faster. Another way we could do this is mg times 3 feet is really 3/8 of L, the length of the board, right? Plus mg, this is really L over 2, right? Minus the tension on the left times L equals 0. And if I write it that way, the L's all cancel. Makes it a little easier. So if you try to do it algebraically, your life will actually be easier, okay, because the L's cancel. So what that means is that the tension on the left will be 3/8 of mg plus 1/2 of little mg. So the cable on the left carries half of the weight of the board plus 3/8 of the weight. Did I do that right? Plus 3/8 of the weight of the box. Okay, does that make sense? And then you can solve it. All right, I'll solve another example tomorrow, and then you guys are going to solve a bunch of these. We're going to apply statics, okay? So finish up that one we did today. Hurry, we kind of rushed through it. A lot of you didn't get the last two. Do that, and then tomorrow we'll do one more example, and then we'll solve a bunch of problems, okay?
Can I also solve the equation?
All right, so here's what we got. Imagine you're trying to hang a sign out in front of your store, right? So you're going to hang a sign on a bar, and what we want to know, anybody on this side here? What we want to know is, what is the tension in this string right here? Okay? So what we have is a rigid object. That's this bar right here. And there are forces acting on it. There's a force going this way, a tension we're trying to find. There's a force going this way. The bar itself has mass, right? That's rotating on me. The bar itself has mass because even without the weight on the end, there's some tension in the string because of the bar's mass, right? Where does the mass of the bar act? It acts in its center, right? So we're going to try to figure out what is the tension in this connecting rod or string right here. Okay, that's the goal of the thing. So I need a little bit of help. Somebody got a calculator there? We're going to have to figure out, I picked up a meter stick and laid it down somewhere. We're going to have to figure out the angle this makes right here. Okay? This angle right here. Okay? So this is a right angle here, true? That's a right angle. And so this distance is, gotta go this way, 75 centimeters. And this distance is 62 centimeters. 75 and 62. You got that, Luke? All right. All right, so I'm going to work through this example problem and see if we can find that tension there, okay? Does that make sense? You can kind of feel it. It's pretty tight. Okay? All right, so here we go. And I will video this so that those who aren't here can watch. All right, here we go. So the first thing we do is we make a rigid body diagram. The rigid body that we are interested in this problem is the meter stick. So here is the rigid body. Now, that rigid body is attached to the board. Are there forces acting where it attaches to the board? So are there any forces acting on the meter stick right here? Are there any? Yeah. board's probably pushing out, and it might be pushing up, I don't know, it might be pushing down, I don't know, okay? But there's forces right here. So there's forces acting on this end right here. So in general, when we draw the forces, let's do forces in green. There is probably some kind of horizontal force acting on the bar due to the wall. So I will call that Fx. There's probably a vertical force acting on it right there. I'll call that Fy. Okay? Gravity acts at the middle of the bar and pulls down. I will call that little m times g, that force. I've got a weight hanging on the very end. Luke, can you see what that is? Is it 200?
I think it's 500, but it's like kind of scratched out.
Okay. So we have another mass acting on the end, pulling down there. And we have one more force acting in this direction, like that, and that's a tension, so I'll call that T. So this is the rigid body diagram that shows all the forces acting on our rigid object, the stick. Okay, you good so far? Now our job is to find the tension here, okay? Let's just write down what we know. Little m is the mass of the meter stick, and it's about 90 grams. I'm going to put 0.090 kilograms. Big M, Luke thinks is 500?
I think, I can't see it.
Well, look at the set, look what's missing. It's 500.
The 500 is missing. Luke is right, that's been kind of... So the 500 is missing, so the big mass is 500 grams. And it helps to know some dimensions, okay? We will call the length of the stick L. Is that okay? So we will call this L, so probably need a different color. So if this is a distance L, then what is the distance from here to here, for example? That's L over 2. Okay? And this distance right here is 1/4 of L. I attached it at the 75 centimeter mark. So that's 1/4 of L from the end, or 3/4 of L from there, right? Okay, so now we can kind of work through what we can do here. Is it true that the forces in the x direction add up to 0? I seem to be missing all my markers. Is this true? The sum of the forces in the x direction equals 0.
Yes.
Well, look at it. Is it moving? Is it accelerating up? Is it accelerating down? Accelerating left? No, it's static. It's not moving. So the forces are balanced. So which forces over here are going up? Who said that? Luke? Is that you? That was you? Matt, which forces are going up?
Tension of the spring.
I'm sorry. I'm doing X.
Oh.
Which forces are going to the right?
The wall.
Okay, the force due to the wall. So F of X. Any other forces going to the right? Nope. Any forces going to the left?
Part of the tension of the spring.
Yeah. What part of the tension? Let's call this theta. Oh yeah, our variable is. We gotta find theta, don't we? Oh, you found it. So a little bit of trigonometry got Luke theta. What is theta, Luke?
34.2.
Theta is 34.2 degrees. Okay, good deal. All right, so minus what, Matthew, I think we're picking on you here. What part of t? The cosine part or the sine part?
Cosine.
We're looking in the x direction here. So we're looking for the part of the tension going this way, right?
Mm-hmm.
And that's adjacent to the angle. So that's cosine. So minus t cosine theta equals 0. All right, does that help us solve for t? No? Ugh, dead end. All right, let's try again. Is that true? It is. What does it mean? Noah, what forces are going up?
The sine of the tension.
Yeah, T sine theta goes up. Any other forces going up?
The wall.
There's a force, the wall is exerting a force, so plus Fy. Any forces going down?
Plus the masses.
Yeah, minus mg minus capital MG. That all equals 0. Can we solve for T now?
Well, I don't know what's going on with the wall forces.
What?
Like, the forces due to the wall, I'm not too sure.
Do we know them?
No,
So how many unknowns do we have?
too many.
How many?
Like 3 maybe?
We have 3 unknowns. Can we solve with 2 equations? No, we need another equation. Okay? We've already done forces in the x and forces in the y. What else we got?
Rotational.
Yeah, not only is it not translating, it's not rotating. So the torques must be balanced as well. Now, you can pick any point you want for your imagined pivot. You can imagine it pivoting around this point right here. Or you can imagine it pivoting around here. Or you can imagine that this is the pivot, and this is going this way, and that's going that way, right? It doesn't matter where you pick the pivot. You can write an equation, but there's some choices that are more useful than others. Do we know the forces acting on the wall? Are we trying to find the forces acting on the wall? No. So if we make our pivot there, we can ignore those forces because they don't contribute any torques. So if I made this point right here my pivot, I'll call it P. Then I can say, Bailey, can you see the screen there? Am I still on the video here?
Yeah.
Okay. So we can say that the sum of the torques must also add up to 0 about any pivot we choose, and I'm going to choose P. All right. So now think about the rod. Here's the rod. Here's the pivot. Does that force contribute any twist? Any tendency to rotate this rod around that point? No, because the distance is 0, right? Does that cause any torque? No. What causes a positive torque? What tends to rotate that bar in a positive direction? The tension. So the first torque is going to be due to the tension. So I'm going to write the tension. Now, here's where it gets a little tricky. Forces are just forces. The torques are forces times the distance they act times the sine of the angle between them, right? So this is going to be the T times how far from the pivot does it act?
3/4 L.
3/4 or L, or 3L over 4, right? And is it perpendicular? No, so we need a sine of the angle between them. That's the positive torque. That is what tends to rotate this bar in this direction. What is tending to rotate it in the other direction to counteract that?
Masses.
These two guys, right? So we're going to have a minus mg. How far from the pivot does that act? L over 2. And is it perpendicular? It is. So the sine of theta is 1, right? Minus big M times G times L. All of that equals 0. Okay? And if we would have started there, we probably would have gotten to the answer a lot faster. Because there are no forces due to the wall in this problem. Right? Okay, so let's solve it. I'm trying to find T. So I get the L's cancel. Every term has an L. Bring these to the other side, and I get 1/2 of little mg plus big mg equals 3/4 of T sine theta. So the tension T is going to be 1/2 of mg plus capital MG divided by 3/4 The sine of theta, I really hate compound fractions.
Yeah, that's not.
So let's just multiply the top and bottom by 4.
Yeah.
Multiply the top by 4 and you get 2mg plus 4mg divided by 3 sine theta. That's the tension. So grab your calculator, work it out, see if we can agree on the answer. Make sure you're in degrees mode.
Are we doing kilograms or grams?
Let's do kilograms. Good point. I mixed my units there. This was 0.50 kilograms. We got to use kilograms in order to get our answer in newtons. So what do you get for a tension T? Got something back there, Bailey?
Yeah, 3.14.
What?
3.14.
Seems a little low. Is that right? Anybody else get that?
I got 12.7.
12.7? Well, let's see. 2 times 0.09 is 0.18 times 10 is 1.8. This is like 1.8. That's 0.5 times 10 is 5 times 4 is 20. We got like 22 in the numerator. The sine of 30 is about a half. That's 1.5. We got like 22 divided by 1.5. That's 13-ish. 12 point, you find it there, Bailey? 12 point what? 12.7 newtons. Now, could you find the horizontal force exerted by the wall?
Yeah.
Well, once you find the tension, you can find the horizontal force exerted by the wall pretty easily, right?
Yeah.
And could you find the vertical force exerted by the wall? Sure, once you know the tension, you know the masses, you can solve this equation for the vertical force exerted by the wall, right? So, the new thing we're adding in here is the idea that if something's in static equilibrium, not only is it not moving, it's not translating, it's not rotating either, okay? And you could have solved this problem if you chose, instead of the pivot on the end, you could have made that your pivot. And it would have worked. You just would have gotten a third equation with 2 unknowns in it, and you would have had to solve this equation for something and substitute it in there. It would have been more complicated, okay? So remember, when you're using torques, if you don't know a force and you make the point where it acts the pivot, it doesn't show up in the equations, okay? Because it contributes no twist, okay? Does that make sense? All right, so that's what we're going to do today. We're going to solve problems with statics. We've got lifting weights, bears walking out on tree limbs, all kinds of good stuff. I think it's there ready to go. So if you haven't got a donut yet, grab a donut, get to work. We will call this now Problem Solving Lab. So if any administrators walk by, I'll say we're in lab now. Is it not working?
I don't think it's working. I'm sorry. Not for me.
Yeah, I see that. All right, you should be able to log in and get going now.
Yep.
If I can cover your diagram with my thumb, it's not big enough. Hi. So what? Did you guys log in?
My students can log in. pull them in or whatever.
How do you get there?
You sent me an email back.
You follow the link?
I clicked your link and then I had it.
Switched password 2 days ago.
Yeah.
It hasn't worked since then, or you haven't tried it?
Well, I haven't logged out of it since then, so last night. My computer was starting to close all the cache and all this stuff, so I restarted yesterday. Yes. That's definitely been a problem.
I updated it everywhere. Do you update it?
There.
Or you save your files inside?
All right, thank you. Sorry about that.
No, it's okay. So we want big rigid body diagrams, guys. I can cover with my thumb, they're not big enough. Draw the rigid object,